So good evening. Today we will design a system in PVSyst. How to design any system in PVSyst, solar PV system in PVSyst. So let us start with what is this PVSyst software. So this is a software package to study and size and data analyze a complete PV systems. So this PVSyst, it is an industry standard. It is widely accepted throughout the world as a industry standard as a solar design tool, and it deals with grid connected systems, standalone system. Like in standalone system, we do not connect it to the grid, and directly we get the supply from solar panels and batteries. And then pumping, for this is for agricultural purposes, pumping systems and DC grid PV systems. So, and also as a software, so solar as a solar PV software, it allows the user to simulate the energy output losses, analyze near shadings, carry out financial analysis, probability reports, horizon profile, and generate many more outputs. And it will help us in understanding the overall performance of a solar PV plant. So to do all this, it includes extensive metadata, and it has some system component databases. Like if you have to design a PV system in a software, and you want to know the performance of that system when it is actually installed, if you want to know the performance of that system, so what will be the inputs? Definitely the inputs will be location details, like what is the location of the latitude and longitude, and what is the altitude of that location. And then what is the weather, like what is the ambient temperatures there, and what is the solar radiation available there. These are the inputs, main inputs. And then other inputs like system component inputs will be what is the module from the market you are choosing, and what is the inverter for grid tied system, what is the grid tied inverter you are choosing. So all the component databases, PVSyst has a extensive database. It has module database as well as inverter databases, and also it have some general solar energy tools. We will see them. And then it is geared to the needs of architects, engineers, researchers, and it is also very helpful for educational training. So now what is this about PVSyst? So what it contains, and this is the one of the most powerful and comprehensive program available, and the whole range of features will be like, it has 3D tools for shading analysis. So we can do, mainly after installing, we can do the shading analysis. And then toolbox for solar geometry. So to understand, if you want to design a system for a particular location, what is the solar geometry there, like what is the sun path, sun position at any time in that location, sun path diagrams. So these toolbox, for that a toolbox is available, like solar sun path geometry we can see in PVSyst. Also extensive meteo database, like I said, we have meteo, whatever in the market available PV modules and inverters are there. It has a database, and if you don't have have the model in the database, if you don't find it, and you can get the file from the manufacturer, and you can just export it to PVSyst also. So, and PV system design, sizing, and operational behavior. Also simulation performed over throughout the year in hourly steps, and complete the report with many additional results. So many what is the performance ratio, what will be the capacity utilization factor, these things also we can get. And then let us start with designing a grid-tied PV system in PVSyst. So I'll just open PVSyst. So this is how the first window, when you open it, so let us start with designing a grid connected PV system. PVSyst allows to design any PV system, any system in some levels, like detailed project design you can do, or preliminary design also we can do. It is just with very basic inputs, it gives the output. But let us start with a detailed project designing in this grid tied system. So let us do a grid connected system. So before doing this grid tied system, okay, before going to grid connected systems, let us see here. You have in utilities, you have this databases. So let us go and check. So today we will design for a system at NIO, that is NIO Goa, that is National Institute of Oceanography, Goa. On the roof of that building, we are trying to design a system, a 60 kilowatt system, a rooftop system, flat roof. And before going to design, what you have to do is, in the databases, you have to include the geographical location, that is Goa NIO location in PVSyst. So now when you click on databases, so just go to weather data. Here you have geographical sites. When you click on geographical sites, you have so many locations included in PVSys database. But if you don't have Goa location, like for India, very few are there in India. If you don't have this Goa location, just go to new. So now it will show us a interactive map here. So just click on NIO Goa and say search. Okay. So location, if it is not found, you can just go to Google Maps. So just take the location. You can just right click and click on the latitude, longitudes. And this will be copied to clipboard. So copy it and search. So here, now you can say accept the selected point. Yeah. So now it will automatically give the site name and the latitude, longitude, and what is the altitude. These are nothing but latitude, longitude, and altitude are the just XYZ axis on the Earth surface, and then the time zone. So for this location, it will give the sun path diagrams. So this is the sun path diagram. That means for that location, for that latitude, longitude, at any time, like see these curves, like for one, it is 22nd June. So on 22nd June, what is the location of the sun? Every time, see, at 7 o'clock it is here, 8 o'clock it is here, like that. And uh, this is the sun position, sun path diagram. So it will give the on y-axis it is sun's height, and on x-axis it is sun's azimuth. That means its projection on the horizontal plane. When if you see the sun here, sun on the sky, and project it down, and then on from the south, from the line due south, what is the angle it is making? That angle is called azimuth angle. These are the coordinates of the sun. So at any point on the sky, for that location, for any time, what is the position of the sun, we can get to know from this sun path diagram. So these are the sun paths for that. And then here is the weather data import. So you have many options here, Meteonom, NASA. So for this location, for this lat long location, what weather data we have? Like, these are the options from Meteonom. Either we can import the data, weather data, or from NASA, or from PVGIS, NREL, Solcast, Solar Anywhere, Solar GIS. So these we can get, but mostly we use Meteonom for accurate data. And some few are like we have to pay, we have to take some, get registered, and we have to pay and then get the data. Few are like that. And NASA, this one is free, but mostly we use Meteonom. And now we can say here import. So now it will be imported for this location. These are for every month, these weather data is imported. You can see here global horizontal irradiation, global diffused irradiation, temperature, that is the ambient temperature of that location, wind velocity, that is the wind speed, and then meter per second, and link turbidity. This one is the link turbidity, means it is the aerosol content present in the atmosphere. It will give the ratio of aerosols content. And then it is relative humidity, percentage of relative humidity. So these are the weather parameters for that location. And it for any units we can maintain, any units you can take, either like kilowatt watt hour per meter square per day, but usually we do we take it in per month only. So let us keep it that way. And now now that the radiation data is imported, so before saying okay, let us understand what are these GHI, what is this diffused horizontal radiation. Let us try to understand this. So when we see the solar radiation, it takes a long journey until it reaches the Earth's surface. So before the Earth's atmosphere, all the solar radiation is parallel, and we call it as extraterrestrial solar radiation. Once it gets interacted, it enters the sun's Earth atmosphere. Mostly it get scattered, and some get absorbed because of the clouds and all, and other aerosols. So that is why as the length it travels more, the intensity of the solar radiation will decrease. And the solar radiation with Earth's atmosphere, surface, and objects are to be taken into account. So now let us see what is direct radiation. So when we see the solar radiation, we have some components in it. The first thing is direct radiation. What is direct radiation? Directly it comes the radiation that has not scattered in the atmosphere, and this is the component that produces shadows. And next is diffused radiation. And this radiation, it gets scattered by the atmosphere, and then it will reach the ground or the surface. And other type of radiation is the small pot of radiation reflected by the surface and reaching an inclined plane. So if suppose I have a solar panel, and the grounds the radiation that is falling on the ground and then getting reflected onto the surface, that is called reflected radiation, or we call it albedo radiation also. And then GHI, that is global horizontal irradiation. That is what we have inputted from Meteonom now. So GHI, it is the sum of direct and diffused radiation, that is this one and this one. Also albedo, also the sum of direct and diffused radiation received on a horizontal plane. So if the plane is horizontal, then what is the total? The total radiation that it gets is called GHI, that is global horizontal irradiation. So now you can understand this solar radiation, direct and diffused radiation, from this diagram. So whatever
you can make
that gets
it on full screen, then explain. That will be better for
sorry.
Yeah.
Yeah. From this figure, we can understand what is direct radiation. So that gets directly onto the surface. We call it direct, and that gets scattered, and we receive it throughout the dome surface. Sky. sky dome, we get diffuse radiation, and then reflected radiation, we get it reflected from the ground. And then now we will understand what is the solar geometry, that is the sun's positioning angles, that is elevation angle and sun's azimuth angle. So what is this vertical angle the sun makes with the horizontal plane is called, that is this angle. If the sun is here and this angle is called altitude angle or elevation angle. And azimuth angle is you just project it downwards, and this angle is called, and to the due south line, this angle is called azimuth angle. So these azimuth and elevation angle give the coordinates of the sun, like position of the sun in the sky. So with just knowing the definition of elevation and azimuth angle, we can say that during a day, like when the sun moves from east to west during a day, during noon time, elevation will be maximum. And at the time of sunrise, exactly on sunrise, at the time of sunrise, it will be 0. Again, it will increase to a maximum at noon, and then again it will decrease and it will be 0 during sunset time. So just by understanding the definitions, we can say the elevation angles and azimuth angle. Throughout the year, it will vary definitely, but just by understanding, we can say this one, elevation and azimuth angles. So again, just understanding the sun's hourly path. So you can see how the shadow is casted here. So how when during sunrise and sunset, the shadow is maximum, you can see, and during noon time, the shadow is minimum. And this is annual sun path, that is throughout the summers and winter, throughout the year, what will be the sun's path, like you can see here the sun's height. During winter, the sun's height is very low in the sky, so that's why we see more shadow during winters. And during summer, the sun is directly overhead, so we get very less shadow. This is the sun path we have seen there. And then the effect of module orientation. So mostly because for Indian projects, mostly because India is located on the northern hemisphere of Earth, we mostly place the modules in facing south. So if we place properly, you can see here, we can get 100%. As the orientation differs, you can see the difference in energy yield. So now let us go with the software. So now we have created a location. Just say OK. So now it will ask to save. So now it has created a file, that is it will save it as MN, that is SIT file. Now say OK. So now after saving, it will ask a synthetic hourly weather data file has also been generated. So whatever data we are getting, so from any weather station, it will take from Meteonom or any weather station, weather input like softwares we get, we are taking. So wherever we are getting the data from, all the data will be monthly data. So what PVSyst will do is, this monthly data, using some algorithms, using some mathematical algorithms, what it will do is, it will convert this data to hourly weather data, and it will save it, synthetic hourly data. It will generate, PVSyst has a tool for this, and it will generate hourly weather data, and it will ask us to save it. So for this will be used in, when you use this weather file, it will be used in calculating the performance of the system. So now you can just say save. So here you can see here, these these gray, white color things are already in the by default it was in the PVSyst software, and these gray colored locations, they are actually created by the user. If any green colors are there, you can set them as favorites, so it will show it in green color. So now you just click on this and say close. Okay. So just now I have created a geographical location here. So I will just say close. Now we are ready to design a project. So just go to grid connected system. So just say start with a new project. So let us design a 60 kilowatt system, rooftop system for the Goa location. So now you can see here, after giving a project name, what it will do, it will hint you in this box what to do, what would be your next step. So now it is asking us to choose a geographical location. So you just click here. You can just select this location, say okay. So now you have now chosen the weather file. Now you have to save the project. So you can just save the project here. So before saving the project, so let us go to project settings. Let us see some project settings. So when you click on project settings, you can see here albedo. So this albedo is nothing but what I have told you. It is the reflected radiation, the reflected radiation that is received onto the surface, which has got reflected from the ground. Suppose if the I am installing my system where the ground is like snow, so white color will reflect more, so that means the albedo will be more in that location. Or we have such a location where I'm installing the system on I'm installing the system on black soil or somewhere like that. So it will absorb more. So albedo will be very less. So in PVSyst also, they have a box here, help box here, usual values for albedo. Suppose it is an urban situation, this 0.14 to 0.22, and for grass, this one's albedo values. So default values is 0.2. You can set it 0.2 only. Let us not change it. And now here there are design conditions. So here it is site dependent design parameters. So in this parameters, just lower temperature for absolute voltage limit. So just say here you have to give the uh, like you can see for Goa location, for that location, what is the minimum temperature during winters? What is the temperature so far recorded in previous like 5 years like that? Say I have the data, so I am giving it as 13 degrees. And these things, winter operating temperature. So what is the winter temperature and what is the usual operating temperature under 1000 watt per meter square? Summer operating temperature. These things you need not change. Let us keep it as it is. So these, why we are giving these temperatures? Because these are required to reference temperature for array design with respect to the inverter input voltages. So when we are going to design a system, what we do is we connect some modules in series, and that we call it a string, and these strings are again connected in parallel, and this becomes an array. This array will go and connect to the inverter. So before doing that, we have to take care that when we are forming a string, that means that we are connecting few modules in series. When we are connecting modules in series, the voltages get added up and the current will be same. So that voltage should be in the limits of input voltage limits of that inverter. So that we should take care. So for that also we have to see that if the with the temperature, the module voltage will change. We have seen the effect of what is the effect of voltage upon the ambient temperature. For in the manufacturer module, when we see the module data sheet also, they will give for every degree temperature rise, what will be the voltage drop, what will be the voltage drop for the module. So that will be given. So the voltage will definitely change with temperature. So for that, we require the temperature details for that location. So just change this one for that location. You can Google it and you can give the temperatures. And then here we have other design parameters, that is array maximum voltage. That is what will be the maximum voltage and what is the standards you are following. Usually we follow IEC, which is 1000 volts, but nowadays it has become 1500 volts. We are getting the module and inverter for 1500 volts only. If this one is 1000 is little, for older modules and all. We follow usually IEC only. Let us keep it like that. And this is temperature coefficient for VOC value. So let us take it from specification, not from one diode. One diode made model means that one PVSyst will perform it will perform one diode model. That is the PV equivalent circuit. It will take an equivalent circuit for PV module, PV cell, and then it will generate the VOC value. Or we can directly take it from the manufacturer specification. And then transposition model for this project. So what is transposition means? So when we are getting the GHI, that is global horizontal irradiation, from any weather input, we are getting the GHI like radiation data. The radiation data will be given as GHI only. Only GHI will be given to us from any weather station. That means horizontal radiation on a total radiation on a horizontal surface. But actually, when we are installing a system, we are not keeping the modules horizontally. We are tilting the modules. We are tilting the modules and we are installing the modules. So what will be the GII? We require the GII to calculate the performance of the system. We don't want GHI. We want the GII, that is inclined radiation, total global radiation on an inclined surface. So PVSyst has a model for this. There are some models, there are some, some scientists, they have proposed some models, some Hay model and Perez model. So usually we can go with any model. If you have a good and sophisticated data, you can go with the Perez model. Or you can go for old and robust data, we can go with the Hay model. So this transposition means that when we tilt the module, what will be the why we are tilting? Because to receive maximum radiation, we keep the module tilted. So that we will, from GHI, PVSyst has a tool to calculate the radiation on an inclined surface. So now let us go with Perez model only. And then it is AC losses power reference. So now we will, this is, we can go with the default values only, that P nominal at PV at STC. And then it is circumsolar treatment. This one also very recently included. Circumsolar treatment means that is also a part of radiation, like the radiation that is around the direct radiation, we call it previously it is included in diffused only. If you want any separate treatment, or you can give, or let us take it as included in diffused only. So now say you have other limitations also, but let us keep all of them as default value for default values only. And this is the project site and Meteo default maximum search area. Like it will, from the project location, from the location details what we have given, it will search for weather stations around and it will take the data. So this is you can limit it for how many kilometers it has to search. So just say okay. Now you can just save the project. So now after, what it will do, it will ask us to please choose the plane orientation. So when we go for plane orientation, you have different types of field types here, like several. So fixed tilted plane, that means the tilt is fixed for the module. Several orientations, like if you have many roofs, like or a dome, that gabled roofs. So you have to give different orientations. And the other thing is seasonal adjustment, seasonal tilt adjustment. You have some ad, uh, provisions given on the structure, so that you can adjust the tilts throughout the year. You can adjust for few months. You can maintain a tilt, and then again adjust it, so that you receive more radiations. Like in solar, if we see during summers, because the sun is directly overhead, you don't have to tilt the module much. Just from latitude minus 10 degree, 10 to 15 degree tilt will be okay. Or during winters, because the sun is very low in the sky, you have to tilt more to receive more radiation. So latitude plus 10 to 15 degree tilt will be fine for winters. So in this way, we have seasonal tilt adjustment also. And then this is tracking. So if you want to go for a tracking PV system, single axis tracking, dual axis tracking, so they are given. But let us now, we are going with rooftop fixed tilt system. So here we have a tilt of 15 degrees tilt. And so before setting the tilt, so you just say, okay. So I have the detail here. So let us see. Just this one. This is the location, 60 kilowatt system. What are the module we are using, and what is the roof dimension, what is the roof height, and what is the pitch we are maintaining. What is the inverter and module we are using. This is the data I have. So now let us go to system. Now we'll have to design the system. So let us say we are here. You have the array, sub array. If you are designing for multiple roofs and multiple location, like multiple roofs, we can say we can design it as or for different oriented systems. So we can define sub arrays. Here see, we have sizing. So enter plant power, that is 60 kilowatt system. So now let us take the module. So here we can select the PV module. So it is Vikram Solar make. And we are going for 330 watt peak module. Three 30 watt peak silicon poly. Yeah, with this Vikram Solar module. So when we select the module, immediately it will give us approximately how many modules are needed for 60 kilowatt system. And then we are going with good V inverter, 60 kilowatt. Just say, and we are having 20 modules in series. So around 200 modules we are using here. So yeah, before just going, I just forgot to give you here. So yeah, Here, when we go to project settings, so we have to give it as 1.3, this limit overload loss for design. So what is this means? This is called as DC to AC ratio or overload loss, we call it. So what this means, what this overload loss or DC to AC ratio means, usually say we have a module with, like, now we have taken the 330 watt peak module. So what is this watt peak module? Like peak power is 330 watts given by the manufacturer, 330 watts it will generate. So under what conditions it will generate 330 watts? Only under standard test conditions. So what are the standard test conditions? They are solar radiation will be 1000 watt per meter square, and the module temperature will be, operating temperature will be 25 degrees and air mass 1.5. But these standard test conditions will not be when you actually install this module in the field. These things will not match. So at any point of time, it will not generate 1000 watt per meter square, and 80 point, and that at the same time, the temperature, module operating temperature will not be 25. It will be definitely more than that. Because of that, at all time, it will not generate 330 watt peak. So that is the reason why when we are installing 60 kilowatt of DC capacity, that means solar modules we are installing up to 60 kilowatt, we reduce the inverter capacity. We do not go for 60 kilowatt inverter. We actually go for, like 30% lesser, for like 55 kilowatt inverter we can go. So that because always the modules will not generate 60 kilowatt. So that is the reason we go for lesser AC capacity. And if there is any, so that ratio, how much we are allowing, that overload loss ratio, that how much we are allowing is called this limit. That limit we are setting here, that is 1.3%. You just say okay and just save it again. So now we have this system details. We have given the module, we have given the inverter, and here is the site. PVSyst has designed this array, module array for you. So this is number of modules in series. That means we have taken 20 modules in series, and 20 each module has 20. Each string has 20 modules connected in series. So 10 such strings are there. So total 20 into 10, 200 modules. And the area, that is active area, or we call it sensitive area, is 388 meter square. So now your operating conditions will be, here it is at 60 degrees, 645. So this temperatures, these operating temperatures should match with the operating voltages of inverter, that is 200 up to 1000 volts. If these temperatures are not within these limits, then it will show an error here. So you have to take care. So this is why we have changed the temperature, like what is the winter temperatures, like that. So you have to take care. You have no errors here, and you can the summary is given here. Total number of modules, what is the module area, and what are the inverter you have used, and what is the DC power and AC power. See, here I have maintained 60 kilowatt. For 60 kilowatt DC, I have taken 60 kilowatt inverter only, inverter. So DC to AC ratio. So now you can say okay. So this is the system design. And now let us come to detailed losses. So now there is a thermal parameter. There are very these losses. First thing is thermal parameters, that is thermal losses. So you can define this. Actually depends on how we are installing the modules, like whether they are freely mounted modules with air circulation, or you have any domes installed, or any semi-integrated with air duct behind, or integration with fully insulated back. Sometimes we install them on the like slanting roofs, which we have the sheet metal roof, or sometimes we go with the on a RCC roof, we put the structures and we install. So in that way, if we let us go with freely mounted modules, so it will directly take the thermal loss factor. And there is also another option here, NOCT. That is, using NOCT also we can calculate the operating temperature of the module. So to get the performance of the system, we have to know the input parameters. That means, what are the inputs? That is the radiation and temperature. These are the inputs. Mainly radiation and temperature we require to calculate the performance output of the system. So this how to calculate the module temperature. So one method we have is NOCT. There's a nominal operating cell temperature. But this method, we usually the PVSyst, it says not to consider it. Don't use the NOCT approach. This is quite confusing when applied to an array. I just want to let you know what exactly it means. What is NOCT? It means it is a temperature given by manufacturer. When you see a PV module data sheet, there will be a NOCT value, like temperature value, NOCT, nominal operating cell temperature, they will give. So what does it mean? Means, so when we have a PV module, like let us write the temperature of a PV module is determined by an energy balance. Let us write an energy balance equation for a solar PV module. So say the solar energy that is absorbed by a module is converted partly into thermal energy and partly into electrical energy. So let us write a energy balance equation. Tau alpha is tau is the transmittivity and alpha is the absorptivity. So tau alpha, it is usually a constant. It depends on the glass cover that is kept on a PV module with that comes along the PV module. So tau alpha is usually as constant, and IT is the total radiation that is falling on a PV module. IT, that this is the input, is equal to one part is electrical energy and the other part is the thermal energy, thermal and electrical energy. So electrical energy is efficiency of the module. We have from the data sheet, we have the efficiency, that is eta, module efficiency, eta C into I total. So efficiency means output upon input. So we have the input, we know the input, and into efficiency we know from the module data sheet, plus UL is the thermal coefficient into the UL into TC minus TA. TC is the module operating temperature minus TA is the ambient temperature. In this we know the ambient temperature, and we don't know we want to find out the module operating temperature. So now what is nominal operating cell temperature? So NOCT is defined as the cell or module temperature that is reached when the cells are mounted in their normal way at a solar radiation level of 800 watt per meter square and a wind speed of 1 meter per second and an ambient temperature of 20 degrees Celsius under no load operation. So under no load, with these conditions, like IT is 800 and ambient temperature as 20 degrees and eta C will be 0 because it is a no load condition. So there won't be any efficiency. Efficiency will be 0. So eta C will be 0. Now we when we measure, when we take balance the equation, when we substitute these values and get it as tau alpha into upon UL is this one. So now we substitute this value here and get the cell temperature. TC is the TA plus IT into tau alpha by UL into 1 minus eta C by tau alpha A. So usually this tau alpha will be given as from bookish equations and all. This is a constant. Tau alpha is 0.9. We can, without any specific more error, we can put it as 0.9. And IT we have we know from here 800. We can all substitute here and we can get the TC, that is cell operating temperature. In this way, so I just told you because I want you to understand what is NOCT, nominal operating cell temperature. This is purely given because by the manufacturer, because we have to understand, we have to know what is the module operating temperature. To calculate that, usually the manufacturer specifies NOCT. Under these, NOCT is also given under some conditions, like we have seen that 800 watt per meter square, and wind speed is 1 meter per second. So under those conditions only, they test it and give the temperature, that operating cell temperature. So usually NOCT will be 45 to 48 degrees Celsius only. So now for using this loss factor only, we are going. So let us not change anything here. Let us keep it as default values only. Next is ohmic losses. Those are nothing but I2R losses. That is the wiring when you are designing the wiring system, like for DC system, what will be there from modules to if you have any SCB combiner box, junction boxes, from junction box to inverter input side, and from inverter output side, we have to design for AC cables. We have to take AC cables. So here you have a tool here to calculate detailed computation, like what is the length, like where you are installing the inverter. You can also have a sketch here. So where you are, so what is the cross section you are using, cross section of the cable you are using, and what is the length required. So all these inputs, if you have a good the system detail, when you go for a site survey, you can just measure what is the distance, and you can just give the inputs, and you can size the cables. So these are I2R losses or cable losses. And then let us not change anything. Let us keep them as default values only. And then is the module quality, LID, and mismatch losses. So now here we have this module quality loss. So whenever we are taking a module, so from the database, we are choosing a PV module. Say we have chosen a module. And when we choose it module, when we see the data sheet, in the data sheet itself, when the manufacturer specify the watt peak, like it is a 330 watt peak module, beside that, manufacturer will give a tolerance for that watt peak. For that 330, they will give a tolerance. So it is the deviation of the average effective module efficiency with respect to the manufacturer specification. So this is the module quality loss. And then is the module mismatch loss. So this mismatch loss, when we are connecting modules in series, here in this system, we have connected 20 modules in series. So in these 20 modules, when we are connecting 20 modules in series, all the modules should be same make, like so from all the modules should be taken from the same manufacturer, and they are all of them should be manufactured at the in the same batch, and under same conditions. They have to be manufactured with all parameters, mostly likely parameters should be there. Only those modules we have to connect them in series, and their their current should be equal, and without any shading. We have to maintain the system. So if there are any mismatches, that will be taken as module mismatch losses. And then it is LID, that is light induced degradation. So this light induced degradation, if you take any crystalline silicon or amorphous silicon modules, for these modules, when after getting it from the manufacturer and after installing it in the field, when you actually install it in the field and start the operation of the system, during the initial hours, of exposure to the sun, these amorphous silicon modules, they will reduce the performance will reduce, and then after few hours it will again get stabilized. After few some time, the performance will be normal, will come to normal. So that reduction in performance, performance is called light induced degradation. This LID loss is only applicable for amorphous silicon modules only, not for other modules. So next it is string voltage mismatch. So the same thing here, in when modules are connected in series, it forms a string. So you have to maintain the current should be same. And when you are connecting strings in parallel, you have to maintain voltage should be same. So all the strings, their voltage should be same. Currents will add up, voltage should be same. So that if there is any mismatch, it will calculate as string voltage mismatch. And then is let us keep these things as default values only. And then is soiling loss. That is the if there is any dust on the modules, the performance will be reduced. So if you have any good value for that, you can just give it, or you can monthly also you can define it. If you have a good data with you, you can define it like during monthly. You can give during rainy season. Usually the dust gets washed away because of rain. So during rainy season, you can give it as 0. So if you have a data, you can give it. So let us not change them. So next is IIM losses, that is incidence angle modifier losses. So let us try to understand what is incidence angle modifier, IIM losses. So IIM loss, it actually, if you see a PV module, so with PV module, we have a EVA sheet, that is ethylene vinyl acetate, like a EVA sheet, that is for encapsulation. We keep this EVA sheet, and then we have a glass cover, and then the module will be framed. So whenever we have the sun radiation coming onto the PV module, what it has, the radiation from air, it will come, it will touch the glass, and then some will be get reflected and some will be absorbed. When it finally reaches, after going through glass surface and then the EVA sheet and then reaching the PV cell, this angle, this won't be the same. The same angle will not be maintained from the time when it finally reaches the PV cell. Some angle will get deformed. So that contributes to the IIM loss. So this is called IIM loss. So we have some models, but let us not go into much details of IIM losses. Let us keep it default only. And then auxiliary energy losses, if there are any auxiliaries like any fans or cooling systems, like for inverter, if you have any cooling system and you want to power them using this system, so you can just add them. But usually for grid tied system, there won't be any auxiliaries. And then aging. So when we install the system, so after a few years, the manufacturer also gives us, so what will be the degradation in the performance after few years, what will be the degradation. So that aging we can consider. Or unavailability of the system. Sometimes the grid is unavailable. Our system, even if the system is producing energy, it can't deliver it to the grid because the grid is unavailable. So in that case, it is a loss, but we can't do on it anything on it. Or sometimes we have any maintenance shutdowns, like that. Every 6 months we may plan for any maintenance shutdowns, like that. In that case, you can update it here, like what is the unavailability of the system. And then is the spectral correction. Usually this spectral correction, it is mainly applicable for CDTE technology. That is, if the module is CDTE modules, then we have to go for it. So no need of going to look into it. So just say, okay, this is about losses. Next is self-consumption. So there won't be any self-consumption for the system. We are directly, transporting the generated electricity to grid. Next is storage. We don't have any storage in this in this system because this is a grid tied system. Next is the horizon. So in horizon, this is the we also call it as far shading. So in far shading, like if you are designing the system in a hilly area or somewhere you have like 10 times more if the area 10 times more distant to the area of the uh, uh, system where it is located. If you have any hills or mountains like that, so you during morning or evening time, you can say that that mountain, because of that mountains there is some um, shade on that. uh, you're not getting direct radiation because of that hills or mountains in between the radiation. So in that case, you call it as far shadings, and you can just get the data from Meteonom. Also, we can just import the data. But right now, or if you have some data with you, you can just give it like this, like before 7 you have for these months, for all these months you have shared like this here, or you can just give the data or just clear horizon, or you can just directly import it from Meteonom or other other data. You can get it from the internet. You can just import it. So for now, we can just say we are just clearing the horizon. We are not taking any far shadings. Just say okay. And now the main thing is near shading. Here we are actually designing the system. So just go to construction perspective. So here we are in this is the 3D layout. Here we can just draw the roof and place the modules. So now let us see, let us first understand what are the options here. So this one is undo, redo. This one is selection by click. This is rectangular selection. This is lasso selection. This one like pan view, and this is rotate view. And these the views, the like 3D view, XY plane view, XZ plane front view, and this is the side view. Zoom, that these are zoom options, and this is the render, like it will show us in realistic view. And then it will show the modules, showing modules. This one you can measure the distance and measure the angle. And again, this will modifying the any selected item. And this is again drawing objects with the mouse. So all these options, view options, XYZ, it will view. And then this is the grid lines. This is the axis, east-west axis. So now let us, here you have tools help here. You can just say create. Now we are designing for a roof, NIO, that is a building. We have the dimensions with us. So let us take elementary shading object. So here we have a parallelepiped. We have the width is, let us check it here. So the width is 15.3 and 54.8. Height of the building is 13.2. So yeah, this is the so now you can say just close the object. So now you have the now you have the building here. So now let's just add some more items. We will see what are other shading, other things we can add here. next say add elementary shading object, select on it. And then you can see here, just we have many options here. You can see surfaces and volumes. See a parallelepiped, square pyramid, triangular prism, hexagonal prism, octagonal prism, portion of cylinder. Like if you have any tanks on it, portion of cylinders we can, and building elements like house plus two-sided roof, asymmetric roof. So we have many options. One-sided roof plus gables, two-sided roof plus gables, four-sided roof, and prism and chimney. Trees we can add if we have any. So just now let us add some handrails for this building. So we have it is 15.3. Let us say 0.75 height and thickness. Okay, number of rungs. Okay, now just close it. So now we have this handrail here. So just select this one and just say modify. So now you have this, you can move it. So just adjust its height to 13.2. So now it is placed exactly. Again, you can just copy and paste it. So and just move it. So the height is same. It is 54.8. And this will be 0. So I'm just placing the handrails on the boundary, like edges of the building. So now I'll just again copy. Okay. So I have to change it, change the length. So the length is 54.8. Now just say this should be azimuth should be 90. So again, just select, copy and paste. So now you can see this is placed. So this is how the the building looks like. So now we are looking to you can even change the color of this module, color of this building. Yeah, you can even change it. So now let's say we are looking to add some modules. So let us select, go to create and go to array of tables. So you have to click on array of tables. So here you can see the modules. So let us say I have like some 28 sheds. So the pitch is 1.6 meters. Shed tilt is 15. So now we'll go for shed size. Shed sizes. So here I want only number of modules in height. So I want only one module, and I want here as number of modules as 7. So because I have to see, this should fit on the roof. So I'm keeping them in landscape. Portrait means it will come like this. So I'm keeping them in landscape. So uh, now we are done with C. This is the table area and this is the shed area. So now I have to see that this required area, that means we have taken 200 modules. So what is the area, total area for 200 modules? It is 388. Like we have the, because from the manufacturer, we get the area of the module. So area of the module into number of modules, it will give the total sensitive area or active area. It is 388.07 meter square. And now we have designed this PV modules here. So how many modules we have, what is the area? This sheds area we have taken, that is 380. So still we are lack with 8 square meter. So now first let us see, let us keep this and do the, now we will do the partition here. So what PVSyst still now know is, it only know the tables. It doesn't know the PV modules. So only tables we have given. Now we will make the partition. Like you can see here, number of rectangles in height. So that is, in height it is only one. That is one module we have. And then number of rectangles in width. So we have on one table, we are keeping 7 modules. So 7 modules, like here we can see 1, 2, 3, 4, 5, 6, and 7. 7 modules. Sometimes like for ground-based systems or some for few systems, on y-axis like width, we take 2 modules on a table. So here we are taking only 1 module and 7 modules for a table. Just to say, all tables of the same size, apply, and just close the object. So now you can see here, now we have to place these modules. Just when the modules are selected, go to move the selection, give the height here, that is 13.2. We can give either 13.2, or you can say like upon the roof we put the structure and then install the modules, right? So let us keep some place for the structure. Let us say it is 13.4.2 meter for structure, and then just drag it here. So yeah, this is how it looks from different views. This is the side view. So now we have some like 380 square meter we have covered. So we still require 8 square meter. That is around 4 modules we need to adjust here. Again, create a table. You can either, let us say, array of tables only. So I want only one. Number of rectangles in height, it is 1, and number of rectangles in width is 4. Now just close the object. So I'll just change it. The height is 13.4. So now you can just adjust it. So now, yeah, so finally, we have finally matched it with the active area, that is 388. So this is how we design. So we design a system, 3D design. Or if you have any, slanting roofs also, we can design it. You can just go to elementary shading object and then choose it here. You have many options here. So this is how it is done. So now I'm just closing the scene. So now after closing the scene, it will ask the shading factor table has not been computed. So just click on the table. So this is the shading factor table. So what is this shading factor means? So that is the amount of shading uh, uh, that is imposed on the system. Total it is the ratio actually, shaded area upon the total active area. Also, in construction perspective, so if you want to see you can go here tools, and if you want to see the shading animation, like what is the shading on the system, so just go here and say day for the year. That is usually it is taken for December 21st usually, because that is the December 21st is the longest shadow throughout the year. On December 21st we get the longest shadow, because it is called as winter solstice. So on this day we get longest shadow. So usually when we are going for designing a PV system, and we are checking the we are checking for shading analysis, doing the shading analysis. So we usually check for the shade, that is the worst situation we will check. That means on December 21st we will check the shades. So let us run the shading animation here. You can see here. Yeah, so actually at 8 o'clock like that, there is shade. And again, after for like 5 o'clock like that, again there is shade. But during peak hours, there is no shading. So just this is how you can see the shading. You can also see like observer position. You can see from any point from where the system you can see. So these are other thing. You have some zone edition, like zone editing. You have some zones we can create, and then we can place the modules accordingly. So this is about the tools here. I'm just closing it. So now I have in 3D design, I have done on the roof for the system, and I have the area matching, like for the 3D scene, and the system design, that is the area, active area. And then we have computed the shading factor table. And now it is how we are doing the simulation. Like this is for no shadings. For no shadings, you need not go and design the construction perspective. And then it is linear shading. So what is the linear shading means? It will only consider the irradiation deficit. Like if when we have mutual shading or any other forms of shading on the PV system, what it will do is it will only consider the irradiance deficit on the system, and it will calculate the output. But that is not actually true, because for PV modules, when they are connected in strings, what it will do is, when there is a shade, what happens, the shaded region that will be bypassed using the bypass diodes. So according to module strings, that means in electrical calculation, detailed in this will calculate the mismatch, module mismatch, and it will give the output. So in detailed electrical calculation, what it will do is according to module layout. So all the modules will be laid out exactly where the shadow is, on which module the shadow is, and where it is exactly located. According to that, it will calculate the output. This is more accurate. But let us now go with according to module strings, and I'm just saying okay. So now we are completely ready. We can also do the module layout, but this will be fine for near shadings. Now let us do the run simulation. So now it is running the simulation. So now here we have the system, the main results here. The system production is 106 megawatt hours per year. Specific production, that is kilowatt hour per kilowatt. That is 1612, and performance ratio is 0.82, and normalized production, that is 4.42. Array losses and system losses are given. So this, we have the report here. So this is the report. So these are all the system summary what we have given. That is project summary, the geographical location, that is latitude, longitude, altitude, time zone, other things. And then from where we have got the data, that is metronome. And then system summary, that is what is the orientation, that is fixed tilt, what is the tilt, and what is the PV array, what is the module, and a total system watt peak of the system. And then what is the result summary is produced energy. This is the 106 units per year. And then specific production and performance ratio. So now let us go. Yeah. These are the general parameters. What is the shed spacing? That is the pitch we have given. So yeah, what is the horizon we have taken? And PV array characteristics. All these are inputs, whatever we have given here. It is showing us. Next is array losses. What are the string mismatch losses, module mismatch losses? Just a minute. Yeah. So this is the 3D design we have done, and this is the sun path diagrams. So yeah. And these are the main results. That is the normalized production for every month. What is the production? That is in kilowatts. What is the production? Next is the performance ratio for every month. Next is this is the result. That is what is the GHI, what is the diffuse radiation, ambient temperature, and global inclined radiation. That is the after transposition. What is the radiation that we are getting for upon a module for a 15-degree tilt? That is the global effective irradiation. And from from array, what is the energy we are getting? E grid, this is the this is the amount of energy that we are transporting to grid. This is the output, like E grid. Next is the performance ratio. This is the loss diagram. So this loss diagram, it will show actually what are the losses and what are the weaknesses of the system design. So mostly where we are losing, like GHI, what we are getting this much, and after transposition, we are increasing. Some energy is increased. So this is the then after near shadings, after IIM losses. And next is after conversion from radiation to electrical energy. So this conversion loss, and again, what is the irradiance level, and then PV loss due to temperature. This will be more due to temperature, much of energy will be lost. And then shading losses, module quality losses, mismatch losses, wiring losses, all these are taken into account. So finally, this is the energy injected into the grid. And next is the daily input output diagram, that is kilowatt hour per day, or upon global incident, like what is the generated radiation and what is the input, what is the electrical energy generated to what is the incident radiation. And next is system output power distribution. So this is also given like useful output system energy and useful out system in kilowatts, and this is kilowatt units, megawatt hours. And this is the single line diagram. So this is all about the system design in PVSyst. So you can just save it. So now you can just change the parameters, like if you want to change the module, or if you want to change the like yeah, orientation, like if you want to change the tilt, like if you don't want to go with 15 and you want to go with 18, just say okay. No, yes, just change it here as well. So say 18, we are going with 18. Close object. And this one also. Just close the object and close scene. So now update orientation parameters, just table. Now say okay and just run the simulation. So now you can just check again what is the output and what is the, you can just save it as, save as new. Now you have changed, you have saved it as new variant. So for one we have put as tilt as 15 degree, and for this we have taken the tilt as 18 degrees. So with different, you can change the inputs and you can save them as different variants. So this is all about designing a system.